This is video 44 in the lecture on the design of reinforced concrete beams. The lecture deals with the design of prestressed concrete in ultimate limit state. Consider a concrete section with prestressing reinforcement with a cross-section of AP, conventional reinforcement at the bottom AS1 and at the top AS2, the eccentricity of the pre-stress reinforcement is E, and the distance from the top fiber to AP equals dP. You can now look at the strain diagram under pre-stress only. Under pre-stress only, we have when the pre-stress is there, the concrete is at the position of AP, the concrete is compressed. This is AC0, it's the compressed concrete strain. The tendon itself has a strain, a negative strain, you can put it this way, which is equal to the force in the tendon divided by the cross-section of the tendon and the modulus of elasticity of the tendon. After that, we can load the beam with the different loads plus the pre-stress. So this dotted line is the pre-stress, and then the loads on top. Then you will see that at the position of the pre-stress reinforcement, the strain is the summation of three strains. Is the summation of epsilon C1, the strain caused by the loads, epsilon CPO, the strain caused, epsilon PO, the strain caused by the pre-stressing reinforcement, and epsilon CO, the strain in the concrete at the level of the pre-stressing reinforcement. By using compatibility equations, you can express the strain in function of epsilon CU2. We know that for the stress in the tendons, when you are in the first half of this graph, then it's EP times epsilon PU, and otherwise if you are in the horizontal phase, then it's FPK divided by gamma P. Once you got the strains, then you can look at the stresses. For the concrete, it's FCD in the compression, then it's sigma S2 in the compression steel, sigma S1 in tension steel, and sigma PU is of course the strain in the pre-stressing reinforcement. And once you've got the stresses, you can convert it to forces. Now let's look a little bit further concerning the displacements or strains. It is strains. Then you see that for the strain you have epsilon PU, the strain at the tendon, at the level of the tendon, is then the summation of those three strains. First one was the strain in the tendon, which is NP, the force divided by AP EP. Then you have the strain in the concrete due to the pre-stressing system and the pre-stressing bending moment. And then we have epsilon C1 due to the external loads. So it's the summation of the three. Epsilon S2 and epsilon S1, it's by similar triangles, you can easily derive them. On the level of the forces, we have the total external load is ND with an eccentricity EP. We will express everything towards the position of the pre-stressing reinforcement. So with reference of this line. So the external forces is ND with an eccentricity of EP. The total compressive force in the reinforcement is AS2 times sigma S2. The concrete compressive force NC is psi BX FCD with delta GX as distance, and so on. Of course, this is only valid for a certain domain, domain 2A here. You can have a similar diagram for each domain that you can come across. And then we apply always the same system, transverse equilibrium, by stating that the external force ND must be equal to the concrete compression force plus the tension in the upper reinforcement. This is a compression in the upper reinforcement, and the tension in the tendons minus the tension in the lower reinforcement. This is compression in upper reinforcement. Sigma PU is of course equal to FPD, and XCP, what we have used here, is just the dimensionless measure X divided by dP. So then you got X FCD times psi B, which is a total compressive force in the concrete. And the rotation equilibrium around this point, it's ND times EP must be equal to those three. It's the external load, this is the bending moment of the compression concrete, and this is the bending moment caused by the classical reinforcement. So you can express an transversal equilibrium and a rotation equilibrium for every domain, and you can do that for every depth of the neutral axis, so for every x. For instance, if you have this can be three tendons in the same section, or there can be more too, it doesn't matter. But now you can write out the equations for all tendons. In this case we have the three. The stress in the tendon is then of course equal to the pre-stressing force divided by the cross-sectional area, which is logic. You can have the different equations. This is the strain and the stresses. This is the filling coefficient, but a little bit written another way. Everything is written in function of the different domains and in function of x, the depth of the neutral axis. So you can continue with all those equations. It looks impressive, but it's not that, it's no rocket science. Then you can have the translation equilibrium, the additional bending moment created by the fact that under the loads, the tendons will have an additional displacement delta epsilon p, an additional strain because of the section, the deformation of the section, and that gives you an additional delta mp. And at the end, you will have then your total bending moment and your total normal force in function of x. And with all those formulas, you create an interaction diagram with on the x-axis the normal force, y-axis the bending moment. And for each x, you plot the corresponding n and m. You have something like this. And then you compare it with the forces acting on your beam, which is n, x, which is the pre-stressing force plus the external force, the external axial force. It can be compression or tension, and then together with the bending moment. the total bending moment, so inclusive the pre-stressing bending moment. And then you get your dots, and if the dots are below the curve, then it is okay. So the ULS check is only a check. It's only checking the capacity by eccentric axial force. In a summary, for pre-stressing concrete, what you in fact do is, with an iterative process, you look at the dimensions of the cross sections, the loads, proper weight, and the pre-stress force, tendon profile, and pre-stress losses. All this takes place in an iterative process. In SLS, you look for the tendon profile with the method of Manuel or with load balancing method, and in ULS, you only check the capacity of the section. In most cases, SLS is dominant. If SLS is okay, ULS will follow. So now you can check a pre-stressed beam in ULS. Next lectures, we will give some 6 examples.